Hello students, welcome to my channel JD Physical Science class. In my last class, I have discussed the conceptual differences between classical and quantum theory. Now, in this class, I am going to discuss the mathematical background required to discuss quantum theory. So, every theory requires a mathematical framework. So mathematics is the basically language of the theory, and quantum mechanics speaks in the language of linear vector spaces. So the language for or mathematical language for quantum mechanics is theory of linear algebra, theory of linear algebra, or theory of linear vector spaces. Now there are four components in this theory, four key components in this theory. One is called states, second is called observable, observable. Third is time evolution, time evolution. And the fourth one is measurement. Now these are the four ingredients of this theory. What is the state? So state means state is defined by a state vector or a wave function. Let us call it psi x. Now this wave function has the all the information about the states. Now, what do you mean by information about a state? The information of the state means what is the position of that particle, say what is the energy, what is the linear momentum, what is the angular momentum. So all the information, possible information a system can have, that is all encoded in this wave function. Now, what are the next component? Observable. Observable means physical quantities. Physical quantities means which we want to measure. I want to measure linear momentum. I want to measure position. I want to measure energy. So these all are called observable in quantum mechanics. So position, momentum and energy. ये सब क्या है? Observable है. Energy and say energy, spin, etc. So these all are the observable. Now, how to get this observable? How to measure this observable? So for each observable, there is a operator is defined in quantum mechanics, and when this operator operates on this wave function, then you get the result of the outcome. That means the values of that observable. Now all these operations are done in using the theory of linear algebra or theory of linear vector spaces. So linear vector spaces. So as I told, इंफॉर्मेशन, सारी इंफॉर्मेशन कहाँ है? सारी इंफॉर्मेशन है स्टेट के अंदर, वेव फंक्शन के अंदर. और हाउ टू गेट दैट इंफॉर्मेशन? वी हैव टू ऑपरेट द वेव फंक्शन, द ऑपरेटर ऑन द वेव फंक्शन. और ये सारे ऑपरेशन, ऑल दीज ऑपरेशंस आर डन इन यूजिंग द लॉस ऑफ लीनियर वेक्टर स्पेसेस. नाउ द नेक्स्ट थिंग इज टाइम इवोल्यूशन. टाइम इवोल्यूशन क्या है? द क्वांटम मैकेनिक्स स्टेट evolve with time, it changes with time. So time evolution is discussed in two ways. So wave function changes with time. So the time evolution of wave function is discussed using time dependent Schrodinger equation. Using time dependent Schrodinger equations. And this is done in the Schrodinger picture. So there is a many formulation of quantum mechanics. Two popular formulations are Schrodinger formulation and Heisenberg formulation. So in Schrodinger picture or Schrodinger formulation, in Schrodinger picture, the wave function psi evolve with time, and the time evolution we study using the time dependent equation. In this formalism, the operators are time independent. That means wave function is time dependent, and operator are fixed in time. Operators are fixed in time. And there is a one more popular formulation of quantum mechanics, which is called Heisenberg Heisenberg formulation. In this formulation, टाइम इवोल्यूशन को हम स्टडी करते हैं. टाइम इवोल्यूशन इज स्टडीड using the studying the time dependence of operator. So in this formulation, what happens? Wave function are fixed. Wave functions are fixed in time, while operator depends on the time. Time dependence operator changes or changes with time. So this will do time evolution of a state or operator. And now the last is the measurement. So measurement क्या होता है? Measurement is different than classical measurement. In quantum measurement disturbs your states. So measurement affects the states. States means affect the state means when you do the measurement, the state collapses to one of the eigenvalue of this operator. Now, what is the eigenvalue? How we do this? We'll discuss later. Now, first, let us take the wave function. I will discuss more detail about the wave function. What is the wave function? So, physical significance of wave function. Physical significance of wave function. Now, if I say take mod of psi x, this is called the probability amplitude. This is called probability amplitude. And the square of the mode psi x square, psi mod x square, which is equal to psi star x, psi x gives me the probability density of finding the position of the particle, where this is your probability density. Probability density. Now, say this is my wave function. Say, let us say this is my wave function. This is my wave function as a function of, say, x. This is my wave function. Now, if I take mod of square, the mod of square will be how? So this everything will become positive. This become positive. This become positive. So this is my mod of psi x square. Now, what is the probability? Probability means this is the probability density. So we are working in a one dimension. So this is the probability per unit length. So say if I take this function, says this one, say this is psi x square. So if I take, say, this area, So this is psi x square, psi x square. And now if we multiply, this is the length psi x square, if we multiply by this width dx, so psi x dx square will give me the probability of finding the particle in distance, say x or dx. So this area is equal to the probability. So this will be psi x square dx. Now probability cannot be more than one. If a particle has to be somewhere in this x-axis. So if I integrate the probability, say psi x this dx from minus infinite to infinite, or say all space, all length, we are one dimensional. So this should be equal to 1. That means my mod of psi x square dx should be equal to 1, and this is called normalization. That means my wave function is normalized. So physical state has to be normalized. That means if they are really physical state, that their probability should be the sum of probabilities finding in a space should be 1. So this is condition is called normalization. Now suppose what happens if this psi x dx square is not 1. Okay, so if psi x square dx is not 1 but has some value, say some constant value, say dx is equal to, say, some constant value n, okay, not equal to infinite or less than infinite, some fixed value, then also it is possible to normalize this state. That means this condition is called square integrable. So if this if I integrate this throughout the space and this value is not uh, diverging, it is a some it's not infinite, then these wave function also are acceptable wave function. We can express, or we can define a physical state using this wave function. Now if so now if I say, if my wave function says psi x is not normalized, then in that case I can take my psi x, say this is the, I'm taking some other function psi dash x. So psi dash x, or is or say psi x, say psi x can be written as a mod square root of n psi x, say the psi dash x. So this is the normalized wave function. Now if I write, say, psi dash x, say say this constant is, say, lambda, and this is the x, where a lambda is what? Lambda is the element of some complex number. Now what this says? This says if psi x is say a so if psi x is a physically acceptable state, and if you multiply that state with some constant, that will not change your physics. So if psi x is your acceptable wave function, if you multiply by the lambda, then the physics does not change. That means we can do, because there is a requirement for normalization, so we can normalize a wave function, and this is also a acceptable wave function. Now let us discuss one more, say, wave function. Say I have a wave function, say one wave function, say psi x, which is equal to e power iota alpha psi x. So now if I take and psi x is the normalized, say this is the normalized wave function, this is the normalized wave function. Now if I take, say, mod of psi x square, because it is a normalized function, this will be equal to 1, minus infinite to infinite. Now what about this psi dash x square? If I take mod of psi dash x square dx minus infinite to infinite, because this is a phase vector, this is also 1. So अगर दोनों ही 1 है, both have a sum of probabilities equal to 1, but that doesn't mean that these two both are the same wave function. They are explaining and they are describing the same state. So even though their probabilities are 1, but there is a phase factor which will change their observable properties. So psi dash x and psi x are not same states or same function or same states. That point you have to remember. If probability is 1, that means doesn't mean the same. Because of this phase factor, there will be change in the observable properties. Now let us go one step further. So let us take two functions which are normalized. Let us take two functions psi1 xt and psi1 xt, psi1 xt and psi2 xt, and both are normalized. So say that means both are normalized means if I take minus infinite to infinite psi1, or if abhi we are not discussing the time dependence, so you can just take psi x. Okay, psi x. So I just take psi x. So mod of psi x square dx is equal to 1 and minus infinite to infinite psi 2x mod dx is equal to 1. Now I'm taking a third component, third wave function psi 3, which is the linear combination of psi 1 and psi 2, where your alpha, beta are some complex numbers. Now we have to check अगर ये भी normalized है, if this function is normalized, psi 2 is normalized, so what about the psi 3? Can psi 3 is also normalized wave function? If psi 3 is also normalized wave function, in that case we can say this also belongs to some state. This also a physically acceptable wave function. So let us calculate now mod of psi 3 square. Now let us calculate mod of psi 3 square dx. So mod of psi 3 square will be what? It will be alpha psi 1 plus beta psi 2 mod square dx. Now I can use a complex relation, complex number relation from that is called triangular equality, that says z1 upon z2 mod is always less than equal to mod of z1 plus mod of z2. So if I take the square also, that also true. That means if I take z1 plus z2 square, that will be also less than uh, mod of z1 plus mod of z2 square. So that means I can write this quantity is less than equal to what? Less than equal to minus infinite to infinite. We have a state, say alpha psi 1 square plus alpha psi beta psi 2 square dx. This should be less than, I'm taking this as a z1, this is z2. This should be less than this quantity. Now let us simplify further. Now if I say I use one more relation, so here one more term will come because I am taking it's a square, because we are taking the square here. I am taking the square here. So this was, I'm writing it again, alpha psi 1 square plus beta psi 2 square plus 2 alpha psi 1 mod 2 beta psi 2 beta psi 2. Now there is one more complex inequality which says that twice of, say, twice of z1 mod z2 is also less than equal to z1 plus z1 square plus z2 mod of z2 square. This can be proved if if I take z1 minus mod of z1. If I take z1 minus z2 mod, this will be always equal to 0, greater than 0. And if I open this one, so I can show that 2z1 z2 is always less than z1 square plus z2 square. And now if using this inequality, what I can write, I can say like this integration is also less than equal to minus infinite. So I can write this as a 2 times. So I'm multiplying this by 2 times. So this will be disappear. So this will be alpha psi 1 square plus 2 beta psi 2 square. Of course, there is a dx. Now this thing already we know, because this is normalized. So this psi 3 should be less than, this is a normalized function. So this will be 2 alpha square, and psi square is the normalized, and this should be equal to 2 less than 2 beta square. Now this is, of course, we are taking the alpha beta numbers, is all of course less than infinite. That means what I'm trying to say, agar you have a two function, both are normalized, तो so their linear combination is also normalized. अगर हमारे पास दो फंक्शन है साई वन साई टू, अगर दो वो नॉर्मलाइज हैं, तो उनका जो लीनियर कॉम्बिनेशन होगा वो भी नॉर्मलाइज होगा, वो भी फिजिकल स्टेट को रिफ्लेक्ट करेगा. That means now this is the property of what? This is the property of vector spaces. If there are if you have a two vectors alpha, say not alpha beta, just take some other numbers. So you have some two vectors, say psi 1, which is the element of a complex vector space. You have another vector psi 2, which is also element of some complex vector space. If I take some combination of that two functions, psi 1 alpha psi 2, that is also a element of some complex number, complex space, vector space. So what is that? What does it mean? What does it mean? That the wave functions in quantum mechanics, they form a vector space. That's why in the beginning I told you that the language of quantum mechanics is linear vector, the language of linear vector spaces, because they follow the property of linear vector space. And here we have seen the superposition principle automatically comes in quantum mechanics. If there is a one state, if there are two states, their combination will be also a state. So let me stop here, and we'll discuss some more conceptual thing of quantum mechanics in my next video. Thank you very much.